This is question 7 on the sample test problems for test number 3. The graph of a polynomial function g is given at right. The domain of g consists of all real numbers, but all important features of the graph are shown. What that means to us is that this graph, we can assume, just continues up forever this way and up forever that way. Part A, on what intervals is g increasing? So increasing means as you walk left to right, it is going up. So as we trace this part of the curve, as we go left to right, it's going down, so we're decreasing there. But then on this part of the curve, we're increasing until there, then decreasing here, and then finally increasing the rest of the way. And so our job is to just highlight those parts where it was increasing. So that was from here up to the top, and then from here forever. And again, when we talk about increasing, decreasing, we generally give intervals, and we only care about the x values. So we're going to take the highlighted parts and just go up to the x-axis. So for the starting point here, going up to the x-axis, that looks like it's at -2. And then from the ending point over here, it's at x equals 1. So those numbers are going to be important. For all the x's between -2 and 1, this function is increasing. So you could either say the x is between -2 and 1, or if you prefer interval notation, -2, 1, and whether you include them or not, it doesn't matter to me. I will exclude them, but you could put square brackets there. And then it's also increasing from this point right here. So it looks like the x value there is 3, and then it increases forever to the right, just going up forever. And so it's increasing from 3 to infinity. And we'll put a fancy union symbol in between, and then I'll get rid of this part over here. So our full answer is those two intervals unioned together. Part B, on what intervals is g decreasing? So g is decreasing everywhere else. So in particular, I'll highlight here blue. We're decreasing from there down to the bottom, and then decreasing on this little piece in here. And again, we're interested in the x intervals. So starting at the far left, meaning -infinity, all the way until -2. And then union, and then it picks up for just that little piece between 1 and 3. C, list all local maxima of g, estimate if necessary. Maxima are just the highest points on the graph. And the only highest point that I see is this one right up here. The coordinates look like 1, 2. And that's the only point that's higher than nearby points. So 1, 2 is the only local maximum. Just to be clear, that is an ordered pair. That 1, 2 is a point, not an interval. The answers up above were intervals. They look the same. Not to say that 1, 2 is the highest point on the graph. For example, here's a point that's higher. But that point right there is lower than nearby points. So we don't say anything specific about this point here. We're only looking at the local max, and that's at 1, 2. Part D, list all local minima of g. So the minima are the points that are at the bottoms. So there's 1 down there. Looks like this is at -2 and -5. And then one more local min right in here. This one will estimate at 3, and then maybe -0.3. And so those are the two local minima, -2, -5, and 3, -0.3. If you had said 0.4 or 0.2, no problems. E, is a leading coefficient of g positive or negative? So looking at this graph, we can see that at the far right, the graph goes up forever. So that's, again, this piece here. And the only way that a graph can go up forever on the far right is if the coefficient is positive. Think about x squared or x cubed, both of which go up forever as you go to the right. Part F, what is the smallest possible degree for g? Okay, a couple of ways to do this. One is good and one is risky. First, we'll do the risky way. I want to think about how many zeros this function has. And remember, by the factor theorem, The number of zeros is the same as the number of x-intercepts. So I will highlight in green. There's one x-intercept, there's another x-intercept, a third one, and a fourth one. And remember that the degree is, the number of x-intercepts is less than or equal to the degree. And so it could be that the degree here is 4. A little bit less risky would be to look for the number of turning points, that is the number of extrema. And we already found here 1 extrema, 1 max, and 2 mins. So that's 3 turning points. And if you add 1 to that, you'll probably find the degree. So 3 turning points means the degree could be 4. Either way, the degree is 4. I said it's risky to think about just the x-intercepts. I think it's easier, or sorry, more reliable to think about turning points, because imagine for a second that this entire graph was shifted, say, 10 units straight up. Just move that whole graph 10 units up, which means that maybe the axes now are here and down here, and so the entire graph is above the x-axis. So how many x-intercepts does it have now? Well, now it has 0. But that doesn't mean the degree has changed. So x-intercepts are risky. Turning points are a more reliable way to think about degree.